So good morning, everybody. Sorry we're starting a bit late. We had some technical issues and we're going to be doing this a little bit differently today. But we're happy to
It's good afternoon for me, and I guess for Raimo as well.
Yeah.
It's even more afternoon for you, or evening even.
6 o'clock, a little bit more.
Or 5 o'clock here.
Yeah. So good day wherever you are, and regardless of the time. So we're welcoming Raimo Lahtinen today to present on Paleoproterozoic tectonics of Fennoscandia. Next week, we'll hear from Fred Boyer, and I'll send the announcement for Fred's talk tomorrow. So to keep us as close to on time as possible, Andre, could you please go ahead and introduce Raimo for us?
Yeah, it's a pleasure to introduce Raimo Lahtinen. Raimo is originally from Finland and did all his degree at University of Helsinki, and his PhD was working on Paleoproterozoic igneous complexes in Finland, and his expertise is in tectonics, metallurgy, and in last 10 years or so, he started to collaborate and work on basin analysis for Paleoproterozoic successions in Finland and in Fennoscandia. And with this, I pass it to Raimo.
Thank you very much, Andre. And I hope so that we can have a beer sometime in Paleoproterozoic again. So here's the title of my talk, and why I show this modified air mag is that in Finland and also in Sweden, most part of the terrain is, of course, covered. We have only 3.6% outcrops in Finland. So we are relying on key outcrops and then pretty much on geophysical data. So here is the list of the co-authors that I'm working, let's say, today. I have been, of course, working with many people before, but these are those people who are involved in the present presentation somehow. So Juha Köykkä, he's an expert in basin analysis, lithostratigraphy, sedimentology, and so on. Mohamed Sayab is a structural geologist and tectonics. Stephen Johnston is a structural geologist and experienced in oroclines. Johanna Salminen is a paleomagnet person, and Matti Korhila is working with isotope geology. So here's the outline. I'm not going in detail. I'm just showing a slide of Fennoscandia that you will see several times. So can you see this?
Yes, we can see your cursor. Yep.
Okay. So if we think about, we are concentrated on the Paleoproterozoic, which is older than 1.7. So we don't discuss Rapakivi granites. We don't discuss younger ones like Sweconormian, Norwegian, or we don't discuss about Caledonites. And of course, then we have most part of this part is covered by Russian platform sediments. If we start, for those who are not so familiar with Fennoscandian geology, we have here Kola, then we have Karelia, and these white dots, they somehow present areas which are least deformed or extended during the Paleoproterozoic. So it means that, like here, of course, these basins, they have been inverted during Paleoproterozoic, but they haven't suffered a huge amount of deformation. And you can see that there are small Archean crustal blocks which have been moving separately. Then you have here also some sutures which we will be talking later, which have been defined by different methods. We will come to that also later. And then we have those possible, what you call microcontinents or continental arcs. And with blue dots, you saw the proposed oroclines in the Fennoscandian. So here is Botnian, then Saima. This is the Bergslagen, and here is the Inari. We will be discussing also this. And Fennoscandia is part of the Baltica or East European Craton. And to some extent, we are touching also and discuss how these have formed or put together. So if we go to the East European Craton, this is an old figure showing those plots. We can see that it is mainly this area here, northeast of the Trans-European Sutu zone. So these Precambrian areas. And there are only few areas where here in Ukrainian Shield and in Voronezh Massif and also in Belarus that they are outcropping. So most part of these Sarmatia and Volgo-Uralia, they are covered by Russian platform sediments. And that's why most of the information from there is based on geophysical data and drill core data. Just to show you also here are those oroclines that we are proposing or have proposed in the course of the time. And here is a new one from Carpathian orocline, which is about 35 million years old. And here it's easily seen the bending because you are looking at the mountains, which a mountain chain which has been bent. Of course, here you don't see anything. The elevation level is in that respect 0, and there's no mountains left. Few words then about the East European Craton is that these are very much based on work of Bogdanova, Svetlana and her, let's say, colleagues and co-workers. And Volgo-Uralia is mainly Archean, not exposed. Then we have Sarmatia. We will come later to this also, but it seems to be that Volgo-Uralia and Sarmatia have been, let's say, accreted or amalgamated about 2.1, 2.07 billion years ago. And then, according to Bogdanova et al., this Volgo-Uralia has been then collided or accreted about 1850 to 1800 million years ago. And here you can see the so-called work by Terentiev and Santos, and you should all look at maybe this one, which is the one of the key element, also what we will be discussing in the East European Craton. That's the Osnist-Mikhailivsk-Moscow belt. We will come back to that later. Then if we think about supercontinent Nuna, Colombia, so there are several models. I'm not going to go through them. And here is one from Åke. Åke is also listening there. And this is maybe one of the early ones also where there were many of those continents put together. That was Kuochun Sao. But what I want here to focus is that Fennoscandia, how it looks like here. If we go to the next slide where we have the one proposal by Condi, we can see again that the whole Svekafenia is non-linear. And we can see the same area here, and it's non-linear. This was already in 2005, when we started to think about these issues. We were looking why the whole of this area don't show any linearity. And this is one of the key questions also in this talk. Because if we look at typically, at least these, or let's say subduction type belts, which especially if they're Andean types or so, they can be very long, several thousands of kilometers long belts. So then we go back, we go start of the Paleoproterozoic in Fennoscandia. So I'm not going to talk Archean, anything else that Archean, what we can see here in Karelia, that shows that after 2.7 billion years until 2.63, there was maybe several collisions, but it seems to be that that was the main period of the Archean accretion, at least in Karelia and also partly in Kola. And then we can see that about 2.61, when we have the carbonatites, at that point, the whole crust was already stabilized. So then there was about, let's say, 100 million years before the Archean crust. How big? Was it the Kenorland? Was it a part of it also? I'm not going to talk about it, but anyhow, there was a large masses of Archean rocks which started to drift. And that was mainly by mantle plumes. Here on the left, you can see the superior proposal where Karelia and Kola are here. And then here is the Matachewan, and here is the Mistassini, large igneous plume center. So this seems to be that it's not a consensus, but many people agree with that. So if we go to that, we can see that actually in Fennoscandia, which is also in the prop model is here, we have lots of these rocks, which are what we call the Sumian rocks, which are typically about age 2.45 to 2.44. So-called, we have that magmatism, especially in the center of this Archean block that we consider that has been the least extended and least deformed during Paleoproterozoic. And then we have huge amount of these layered intrusions with different ages from 2.51 to 2.44, which is mainly of the age of these rocks. So this shows that we have in these areas which are very much reworked during Paleoproterozoic, we find small pieces of layered intrusions like here in Jumalniemi. But otherwise, it seems to be, it's difficult to say, is it so that there hasn't been those, or is it such that they have been totally reworked and eroded? So then we go to this model wise. So you can see here now we have taken those pieces like Norrbotten, Kola, Karelia South, Karelia North, and Pudasjärvi here, which is here. We have taken those separately, and we have them slightly rotated them. This rotation 35 degrees is from Davy et al. And we wanted to do this so that we could see how well we can match with the Ernst et al. Giant radiating dike swarm trend, and then the circumferential dike swarm trends like this. And this fits rather well. And actually we have a new data from here following these and these granitones until here. So if we look at that model and also these volcanic rifts and areas, it seems to be that they fit rather well for the 2.44 Matachewan plume center, which would be somewhere here in this picture. We have also here older ones, and they are very few. We have some trends like in here in the Norrbotten. We have the so-called Tjohko-aivis. And so, but as I have put here, or we have put here, we have these two locations based just on this data, what we have here could indicate two different places far away where the plume center could be. So the model is pretty much for the Matachewan type is that we have first the Sumi system, which has the superaerial magmatism, and then followed by the so-called Kuusamo system, superaerial to aqueous system. And then this later one is considered that we have a very short plume magmatic period, which is about 10 million years. But then there is a very primitive stage, which comes from the final gravitational collapse of the mantle plume. So in a way, considering all those references that I was referring to, there's a huge amount of work done on these, and this seems to be as well how you call as well known as it is possible in the Precambrian time. Okay, then we go further to the time period 2.4 to 2.15, which we will not discuss too much, but we are showing here the Hanski-Melesnik work from where they have used the term system or chronostratigraphic system with Sumi, Sariola, Jatuli, Ludikovi. And especially the boundary between Jatuli and Ludikovi, that's really varying from place to place. Some people in Russia discuss about 2,100 million years. Something here up north when we have the 2,150 million years rocks that they are already could be considered as Ludikovian. Before we go further, I'm just showing one issue that they were using in this very good paper. They were using this base map from Koistinen et al., which is, of course, that's superb. That's one of the best things that I know that so many countries can agree and produce a good geological map. But at that time, digital circum data was very rare, and most of the correlations here in what I call Karelia Norrbotten boundary, they were made based on the, let's say, lithology. And that's a little bit problematic. So if we look at this part, and you can see that there is about 15 samples from this area. And all these rocks, which are here dark blue, they have been considered as Yatuli rocks. And that's really an issue that I took the first sample in 2008 from the outcrop, which was the classical Yatuli outcrop from Western Finland. And all these samples, they have maximum depositional ages below 1.92. Typical Yatuli orthoquartzites and quartzites, they have only Archean circles, nothing else. But these are these red ones, and you can see that there are some rocks which have about 20% of Archean and 70 to 80% of Proterozoic detrital circles, and nearly half of them are about 1.91 to 1.92. So they don't have anything to do with Yatuli or anything related to those rocks. So they are totally younger rocks. And this is really problematic, especially in these areas like this boundary, what we consider as a diffuse cryptic situ zone. And it's recording about 200 million years of tectonometamorphic evolution. And there are rocks which are very close to each other, which can have totally different maximum depositional ages. So then if we go back to this 2.4, 2.15 period, of course, there are this Lomagundi Yatuli event. And those who heard Anthony Prave's talk on this, and he also in his publication, he's putting that those very positive values are limited largely to nearshore marine and coastal evaporitic settings. And in a way, at least in this area, that's correct. We have only very, very shallow water sediments in that area. And I'm not, how you go, but another thing is, of course, that if we think about how large this is, so we find it here, here in Onega, Imatra, and in these. So it has also something to tell us in any way. If it is, I'm not an expert on this, so I can't say what it is, which one, but I believe that to some extent, Anthony is correct. So then we go to that time frame, which we consider is that when everything into Archean finally started to break up. And if we look at this map here, we have here first of these huge amount of 2.15 to 2.12 volcanic rocks in the Kautokeino belt, also some of them in Sweden, which have been dated. Actually, there is missing, it's the reference. And then we have some dikes about that age here. And that's probably some kind of onset of the break off. But the major break-off is probably happening between 2.1, 2.05, when we have these Kiihtelysvaara. Then we have here Siilijärvi bimodal OIB, Ocean Island basalt type rocks, Otanmäki alkalic rocks, Kiiminki around 2.1 rocks. These are 2.05, these are 2.05. And then we go to Väystäjä, which is rather well dated to 2.08 to 2.05. And that's a trusted package, and which has been at least in shallow marine or maybe a little bit deeper marine environment. And of course, here we come to this Jätuli excursion problem, is that here the age fits to the chains to about 0 values, but at the same time also the depositional environment is totally different. Then we have these large areas where we have these so-called Ludikovian type rocks, which are going also to the Karasjokbel, Petsenga, and so on. And these are characterized here about 2.05 komatiites, which are very common, especially in this part. And that's exactly the same age as Väystäjä, Otanmäki, Siilijärvi, and close to Käymäjärvi, which are totally different. They are ocean island basalt types, rifting, rift-related mantle plume system. So we consider these rocks here to represent the Archean crust breakup and formation of volcanic passive margin. So it means that we will discuss that a little bit later, or it's here actually, sorry, that these are like magma center formed due to small convection cells during continental breakup. They have about, sorry, 100 and 150 kilometer separation. And so between them, there should be only some dikes, and these are those main magmatic centers. And of course, if they would be preserved, we should see one here and then somewhere here also. So this is, of course, like Jeffrey is saying, that there's the volcanic passive margin and then typical normal passive margin. They are end members. So we have, in a way, all the parts here are looking more like a typical passive margin. But after this, there was maybe 50 million years of lull in at least in the magmatism, and then about 2,000 million years ago, we started to get a lot of bimodal magmatism here in the central Lapland, in the central Lapland granitoid complex. And we have also here, I haven't marked them, but we have carbonatites, which are 2.0. So that seems to be that that's again, is that partly due to drifting, so that there's something, because these are not in the place now, so they have been here farther away. It seems to be that there have been possibly a drifting episode producing then these melts. And then this has continued, and we have then finally the Jormua-Outokumpu ophiolites. And these ophiolites are such, like work here is work by Peltonen and then Continental, that they have very good preserved mantle section, but the mantle is Archean subcontinental lithospheric mantle. So it hasn't opened so much that there would be depleted astenospheric mantle where the small amount of below lavas have been going on. So it means that we have had all the time first a breakup and then continuous drifting forming marginal basin. Okay, then we have now breaking up the, let's say, at least the Karelia and probably also Karelia boundary. The Norrbotten is a little bit more problematic, but then we have some indications of so-called archetype rocks which have been preserved. If we consider the oldest ones are those from Kittilä, where we have suprasubduction ophiolites and boninites. Then we have some in Tersk. Actually, the age range would be maybe 1960 to 1940. And then we have the so-called Inariak, where we have close to and above of Archean rocks, we have very juvenile island archetype rocks. And then we have the Naften. Of course, it's not so big. We have 2 occurrences of that, which is 1950 to 1940. Then we have the so-called Savoark here. So these are showing that there has been evidence of subduction type magmatism around 2.0 to 1920 million years. Then there are also proposed so-called microcontinents or continental arcs, which is the Keitele and Parislaken. They have infrared ages. Then the Botnia might even include Archean crust that was proposed by Anderson 1997. But we don't have any direct evidence for this. It's mainly based on isotopic interpretation and seismic data. So then we go to the sutures. If we think about the sutures are of course important, that if they are true, they are representing plate boundaries. We start with, of course, maybe this famous one, because there we have eclogites. And eclogites, of course, they indicate that at least something has happened, like in this case, that continental crust has been taken down to 70 or even 80 kilometers depth. But there's a lot of debate on the age of eclogites. Some consider them solely Archean, some consider solely Paleoproterozoic, and some consider that they are both Archean and Paleoproterozoic eclogites. And especially if they're in those ones which are those most definitely are 2.1 dikes, if they have eclogites, turn to eclogites, that indicates Paleoproterozoic. The latest study from Lee et al. This year concluded that at least Salma eclogite, which is here, record cold subduction, and these peak conditions would be meaning something like 70 to 70 kilometers or more. What other things what we have here is that we have northeast-American thrusts and nappes towards the foreland, which are, and then we have here in Inari, we have southwest American thrust systems in the Red Rock Basin. Then we have maybe the most, let's say, controversial Sutu, that's between Karelia and Norrbotten. There are, the main reasons are that we have about this size each Vergen fall and fold and thrust belt. So it means that there has to be at least opening of hundreds or few hundred kilometers. There are, as I said, there are suprasubduction ophiolites and boninids. And then there's also indications that the mantle on this side is totally different from this side, which could indicate that they don't even have ever been touched together. Then we have this Rahel-Aadoka-Suture, which is the very, let's say, well-known, although still debated suture, where there's a very sharp change from Archean to totally juvenile 1.92 rocks here. Then there's the Jormua-Outokumpu suture. Some people could say that you can't even call it the suture because there is no subduction. But there is rock, graphite-bearing rocks going down under that, indicating the collision, later collision. And then there are these other sutures. They are inferred from geophysical data, different types, and for this magnetic telluride data, here we come later. And these are many then are of course also debated, because we don't have in this area, we don't have any evidence so far of any cold type subduction. I'm sometimes mentioning some so-called tectonic events or structural divisions on tectonics events, what we have done. And I'm not going to go them very detailed, but the one issue what I want to say that every of these D1, D2, they can contain different deformation event. So in an old classification, you could separate them D1, D2, D3. But as far if we consider that they are part of the same system and the shortening direction stays the same, we then consider then A, B, C, or so on. So what we have here is this the D1, which is related to collision between Karelian and Norrbotten, and then this part, and so for Kola and so on. And these are for that reason that otherwise it's almost impossible to discuss structural information from different areas if we don't have something that we are, let's say, using as an leveler, although it doesn't mean that that's correct, but at least it means that they are in the same way wrong then in that respect. So a few words of the Lapland Kola origin. So this is from the work 2019. There are similar models. Then there are alternative models where the subduction is put here. So on the totally on the different side. And here you can see that we did try to also look at how the eclogites go form here below the crust. Then they turn to granulate phases and later to amphibolite phases. This is based on the evidence that was gathered at that time. One of the important issues here is that we have lots of the so-called apinites, which are intruding these recumbent folded Lapland granulite belt rocks. So indicating that D1 has happened before 1905, probably already 1910 or even earlier. So there's a rather good age control on these issues. Then there's also shown the model for the so-called Inari-orocline, which is look like a parallel type fold, but when we come back to the so-called main orocline states, this is probably still younger. So main part of this has started to acting partly ductile after being heating about 50 to 80 million years. So it's it was how you call acting competent when the main orocline stage was going on. Then we go to the Svedkofenian origin, and we were showing these island arc, and then we have here the so-called magmatic flare. If we look at this part of the Svedkofenian, we have the most important archetype magmatism was about 19.0 to 1.88. And it's about the same age from here, here to here, 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 and the Perislagen. And it's really important to understand that that's rather short. It's about 15 to 20 million years, which is in a way, it is a magmatic flare by definition in that way. And this also shows that if we look at, this is the data from Hanno from more than 10 years ago, but this shows one issue, what is the peak of the Svedkofenian orogeny? So it means that on this level, we have a huge amount of rocks which are either about this age or 5 to 10 million years younger. So they are, let's say, arc, syn-arc, post-arc, syn-collisional, and then post-collisional type. And this is the data from Åke's work. And you can see that you can just see this 1895 peak, which is related to this magmatic flare. And then there's a huge peak in 1880. And then there's a huge, smaller peak in 1795, which is related to this tip, very much to the tip magmatism, and very small of these older ones, which are very random. And then if we go back, we have to think about this, what we see here. This is a very peculiar issue, is that we have detrital circons seems to be mainly coming from some different source, at least compared to the present level, erosion level. Then I'm just showing a few figures of the plate tectonic models. And I have to say that most of the early models, they were focusing here in Finland from Archean to Proterozoic boundary in this part. And the first one was Hietanen in 1975. He was working, if I remember right, that was in California at that time. And she was adapting the model from there. Then we have maybe the most cited one is the Karl and Korpachev model, 1987. But these times, it was also the time when uranium-lead circum work started to bring some information about the age of the rocks. which changed then many things. And also there were other isotopic things done. Then in 90s, you could call that was a decade of geochemistry. So there were different types of models which were based on different geochemical aspects and so on. And actually, it was funny that then Gabor changed in 3 years the whole figure, so that now the subduction was to the southwest first, and then there was a subduction reversal. He was doing that based on the work of Ward and also on the work of Matti Vaarsioki and others, which showed that these parts are juvenile. And then we had 97, the work by Mikko Nironen, which was very much how you call the inspired by the work of Hamilton in the Marianas and there. Then we go to the 2010, and I have put this as a decade of accretionary origins. So we proposed of the model, and then in 2008 and then on, from work done in central Sweden, there was a change to this migratory tectonic switching model, so that it was an accretionary model all along from the Archean Proterozoic boundary down to the southwest Sweden. So if we think what is the situation now, we have models which are solely southwest retreating accretionary origin model. And it has been said that maybe 2,000 million years, everything has been in the same direction. And there has only been different tectonic switching and so on. And like the very good book by Stevens and Bergman-Weihed from about Swedish geology, they're all the things, the models are based on this. Also, Bogdanova used the accretion origin, but only for the southwest part of the Fennoscandia. And then there's our model in 2005, which Mikko and then some others changed, but the basic idea was also the accretionary, including also on collisional states. And then there is this model where the orocline forming events are very important. But if we start with the Svekofenian origin, we start from the north, which is this part here. This is a model that we have proposed there. And I'm not going to go to details, but you can see that this is the area where we propose this 600 kilometer long and 300 kilometer wide foreland and fold thrust belt. And then there are different stages of this, but we don't go into this detail. And then if we go to the Svekofenian origin central, so this is the part where most people there has been huge amount of people working. And this is based on what we did in 2000 last year. So the main issue here is that we have first a collision, shallow slab break off, and then rifting forming most of these MORP, EMORP type rocks, then subduction reversal like Gabor Gaal had, and then collision, which is our D2, and then this orocline stage, which formed this system here. And here is shown the arc magmatism, which is about the same age, going like this. So how we came to propose the orocline system is that if we look, the main issue here is that we have the conductor anomaly, which is dipping like that, which is going to the depth of 25, 30 kilometers or even 40. And if we take the interpretation that it means like strongly sheared graphite bearing rocks, that means a plate boundary, some kind of plate boundary. Then if we look at the rocks around the so-called Karelia or Central Finland granite complex, we can see the yellow ones are these volcanic rocks, which are about the same age. They are going like this. Then the structural vergence is here like this, like that, like that, like that, changing across the proposed orocline. And that then we proposed this sketch at that time. Then we also were thinking how it continues more to the south. And then we followed and actually studied the area and came to this model, which is then shown here. So is this the only model type? What we were, because we were looking at Archean parallel buckling, partly as the case. No, there are other models which have been proposed, like for the New England origin here, which is mainly a slab rollback model. Then we have the, I think so, the David, I was seeing David also. Yeah, David proposed intended tectonics model, where here is the Trans-Hudson, you could call that the oroclinal bending. And then we have a complex slab rollback plus intended tectonics model by Morrissey for Tasmanics. And all these models seems to be that they have, this model has to be over 30 million years take. Depends on how you think. This can be 30 to up to 70 million years based on the presentation. And this needs about 50 million years. But we have rather well dated that this is about 10 million years. So we consider that the Oregon barrel buckling is the fastest way to do it. And that same shortening we see also on the cover rocks here on the Archean side. So in that way, it's difficult to put it in this model. But anyhow, at this stage, the most important is that the orocline is there, and we prefer the Oregon parallel buckling model, but there can be also other models. If we go then the continuation, that's the problem we come here. So what I have been working on lately is here. So how we see that if it goes like this, where it ends. In this part, what we see, it is well dated. Also here, it looks like that the dating fits well. We see nearly orthogonal system and much of type 2 fold interference patterns. Then the question comes, what is how much there is crustal decay buckling, how much there is a layer parallel shortening, maybe detached from the middle crust. And then there are also basin inversion, and then there are some northwest Virgin thrust and folds. And so that the thing is not so easy, there is younger system which is having the same similar trend. And especially here, it looks like that we can't say that it's lithosphere scale or crustal scale buckling solely. There is aspects of collisional shortening at the same time. Then if we go to this continuation of the Sarma-orocline, we come to the problem that the Perislaken and Uusimaa belt, they are very similar. Age, lithology, ore types, everything. But in that area, we have the youngest deformation is our D3. That's the same situation that we have here, but it don't have anything of those deformation that we see here. And also the Peuk and Kuiper say that the orocline formed here at 1820. So it might be so that it has been separated from Uusimaa during this orocline, main orocline stage. Then we are going then to look at the post-orocline stage, and I'm here using the work by Svetlana and showing that how her team divided the rocks. And at this stage, I don't have anything to say on those. And here is the so-called Sarmatia boundary. I'm not going to go to those details, but let's go to one issue which is maybe important, is that what is the Fennoscandia and Volgo-Uralia Sarmatia or Valko-Sarmatia? So we have this model where it is said that about 1800 it has docked. In this Paleomag model by Svetlana, they are putting a counterclockwise rotation, and so that this would happen around 1750. Then we have Sven-Åke Elming's model, where we also paleomagnetic model, which is clockwise rotation of the Sarmatia, and so that they are separated. And we are just now, or Johanna Salminen is just now working on this, and the preliminary results, when we are using new data, indicates that this model is not eligible, and also we have to change this. But anyhow, there is clockwise rotation. The one issue that what we saw already is that in Finland, in these areas, both on the Archean part, Archean cover, and on the Svekafennian, we have rocks which have huge amount of 1980 to 2000 million year detrital circles. I'm not going to go, but this is from the paper where it has been proposed that there is a cannibalistic recycling of the material with adding a little bit new material and so on when coming from the so-called Uppekaleva rocks from the Archean cover to the Svekafennian. But the main thing is that this is the only place at this stage where we have rocks which could be a major source for this. So assembly of the East European Craton, it's we have here rocks like this Teteriv orogenic belt and this East Volga-Don orogen, East Sarmatia orogen, and all this shows that this whole system most probably didn't have anything to do with the Fennoscandia before or 2.1. But then we come to this interesting thing that we have this Osnist-Mikachevi-Moscow belt, which borders both parts of the Volgo-Sarmatia. And as I said, we propose that some of the material, what we see here, is coming from this. So that would indicate that there has been some kind of collision already 1930 to 1920, and then followed by some kind of clockwise rotation. And also to understand the whole system here, we should think how we form these oroclines. But many things are here which we could say that it's working in progress. I think so that I have been, maybe I skipped this part, or you can just see, this is one where we are just comparing, let's say, the southern Greenland. And you can see that here you have eclogites, here you have eclogites, here you have eclogites. You have the similar type. I have rotated them to show that they somehow fit, that this could be a continuation. And you can see also during the D2, the orocline, D3, but this would mean, and also this D4-1, and then to D5, and so on. And still there is something what has been noticed in the West Tromsø basement complex, which is, and also here, which is at least young as 1740. So I think so that I leave it here, and here are the concluding remarks, and I'll leave this, and if there's some questions, I'm happy to answer. Thanks, and sorry about this hassle with the start.
No worries, can happen to anybody. But thanks for the talk, Raimo, really good. So we'll go ahead and start with the question and discussion. You can ask in the chat, and I can, by typing it in the chat, and I can ask it for you, or you can raise your hand virtually with the reactions button below at the bottom of your screen. But I have one from the middle of your talk that was sent to me, Raimo, already. How did volcanism vary across the drifting episodes? Was asked 20 minutes ago. I don't remember what slide it was, but yeah.
That's probably, that's what, it's that the rifting 2.1 or what?
From case under SAR1, sorry, case under SAR1, if you want to clarify. He might not be here anymore, actually. Oh yeah, he is here. Okay, he says yes, asking the 2.1 drifting episodes.
Yeah, it means that if we look at 2.1 to 2.05, the thing is that in the 2.1 system, in the center of, if we look at this area here, we have tholeitic magmatism, which have almost juvenile system. So it indicates that there has been, at that point, some pathways to come without contamination. But then if we look at 2.05 in this area, in the central part, like Kevitsa intrusion, it's totally contaminated, which can be seen in all the isotopic indices. So it indicates that either it has been staying, the magma, already a long time at the lower crust, or during the intrusion, it has been forcibly and strongly contaminated. But then when we go to these 2.05 rocks close to the proposed Sutu, they are ocean island basalt type rocks. So very juvenile, without any indications of strong contamination. So they seem to be both the felsic and the mafic rock seem to be coming from the mantle plume.
Okay. All right. Next, we have a question from Aki Johansson. So go ahead, Aki.
Okay, I guess one question and one which is more of a comment. The question which you may not be able to answer and maybe just throw out to anybody here is, say at 2.1 or 2.0, when this rifting, I guess, occurred along the southwest margin of Karelia, what was sitting on the other side, where now you and me are sitting in the Svekofenian part, but then the Svekofenian part was not there. So was there an open ocean, or it was something that rifted away? So it would have been some other Archean Craton, presumably, then, that rifted away and is somewhere completely different place of the world now. But on the other hand, it couldn't have moved perhaps away too far, because then the ocean started to close just some 100 million years later. So do you have any idea of what was sitting where is now southwest Finland and most of Sweden? What part of the world was sitting there in those days, or anybody else has any idea about that?
I don't have any, but if you think about that, if the final breakup happened 2.05,
yeah,
and then the collision was 1910, 1920, that means that it's 130 million years, which means that it can be 1,000 to 1,500 kilometers. Of course, if the bees has been going away, then the other part. So it is difficult. It is difficult, but I can't say to that anything. And it's problematic, of course, that if you want to correlate something, you should have something very good markers. And at least as far as I know, I don't think so that the Karelian Archean has anything so special.
But it should have been a piece of Archean continental crust, not an open ocean, you think?
And of course, all the way, the problem is that what happened, if you think about the Sumi system and this Matachewan system, that should have opened also the Karelia from the north.
David, did you want to add your comment?
Yeah, well, the comment then would be towards the end now, and Sarmatia is probably, as I would see it, it's kind of closing in and coming in like a kind of bulldozer or snow shovel, I said. But then South Africans objected and said they don't know what a snow shovel is. But since we had this heavy snowing now here in Sweden, and I guess you had it in Finland also, you could think about Sarmatia as a big snow shovel, and it shovels all the stuff that's in the ocean between Fennoscandia and Sarmatia. So you could think that what is now the Svekofenian arcs, they were not just coming from the southwest, but rather from the southeast, and originally maybe sitting in the ocean, almost outboard of Sarmatia, parts of it, and then being kind of shoveled and buckled and ending up in a kind of square-shaped area in between Sarmatia and Karelia that now forms the southwest part of Fennoscandia. So that's why there is such a wide area of continental crust, or Svekofenian continental crust, which is not elongated, but it's kind of piled up here. And why you have this so much of crust apparently forming in such a short time, around 1.88 to 1.90 million years, that is kind of shoveled coming from the southeast somewhere from in front of Sarmatia and piling up here. Or what you say? And maybe those kind of oroclines and buckling are part of that process. I don't know, but
yeah, actually, I'm just working on that problem, and the one issue there is all the time is that is it so that Sarmatia have rotated significantly after 1800? So then we are in a problem, because then we have to understand how we can rotate so much if we don't see any real subduction system at that point. So it means that we have to then either think that Paleomagny is not correct, or we have to think something else. But anyhow, in a way that you are correct, that if we think about the Sarmatia issue is in there are some new evidence from the Devonian kimberlites, which indicate that from the known Archean crust in Sarmatia, there is 200 kilometers to the west, there is Archean basement. And either it is the continuation of the Ukrainian shield, or it is part of the fragments from the Karelia.
Okay. Yeah, David, you're certainly welcome to chime in. Oh, he needed to go. Okay. Well, David mentioned, he said Davy plus 20 would have the other rift margin as with the Wyoming Craton, and he thinks that's quite possible.
Okay.
Raimo, I have kind of related question. I mean, it's sort of traditionally accepted that at 2.1 was breakup and rifting in Fennoscandia, and and it's based mostly on magmatic record. But if you look on sedimentary record, it actually there is no evidence for rifting at that time. What you have before it, you have marine Aetolian, and you mention a tidal signature and marine signature. And at 2.1, there is a transition flooding, and basically it's drowning of carbonate platforms. So it's not really a signal of rifting and breakup. It's rather maybe distal response to some tectonic events somewhere else. So if you have any thoughts on it?
The issue is that on the western margin, it's the problem is like in this area is that actually we have very little of that time exposed, because this part of the crust has been thickened double or triple time what it has been when it was extended. And then when we go to the Siilinjärvi and we go to Väystäjä, we start to first see thick turbidites, thick-bedded turbidites. And that's, I see that there is a change if we look at this area here in the middle of the central Lapland, we have to go here before we start to see any of these, let's say, about 2.05 or 2.0 age thick-bedded turbidites. So it's I understand your point, but at least these issues, and also that we have these rocks which are totally oceanic like going like this. That's it doesn't prove it, but at least I consider it as let's say some evidence for the breakup.
But could it be a breakup early and it just reactivation of passive margins?
Yeah, of course, that's all the time is that if we look at those 2.4 layered intrusions, which goes like this, they stop here at the end. So someone could say that there has been an opening already 2.4. And also if we look at the whole system here is that we see few slices of trusted rocks. So we don't really know how far all the systems have been. And that's the real problem all the time when we are dealing with the so-called cryptic sutures. It's the same if you go here, like here in this Fennoscandian origin. You don't see anything here. You find some eclogites, and then you have some subduction, possible subduction type calc alkaline magmatic rocks, but you don't have anything else which would be clear evidence. So that's really problematic in the Precambrian. As I said, at least this area, it has 200 million years of tectonothermal reworking.
Thanks. Just to switch, what is the contact between northern and southern Karelia? Like you have double dot line, where is it a suture, or you also your reconstruction between northern and southern Karelia?
Ah, okay. This is the what's the name? This is the Kukasjärvi southern Kuusamo system, and because otherwise in the whole Kuusamo I don't see anything shortening in this direction. There is this area which continue to the Russia in the Kukasjärvi structure. You know that structure probably well, which is also squeezed between two Archean blocks. And the issue is that at least some Russian colleagues even think that it might be so that some of the rocks there could be ophiolitic rocks, which could then make it so that it could be a continuation of the Jormua-Outokumpu system. But I don't know. But that's the thing that what they are proposing.
Okay, thank you.
Okay. Do we have anybody else who'd like to step up and for discussion? I'll give a few seconds.
So another question, like in terms of comparing Fennoscandia and Greenland, the sedimentary record seems to be very different. So there is no equivalent of Sumian or Etulian or any, or at least reported Paleoproterozoic glacial events. I mean, maybe it's a different erosional level, but sort of sedimentary parallels are not very strong.
Yeah, I'm not on how you call. I'm not an expert on that, but I think so that in Rinkian belt you have some.
There are young Paleoproterozoic sort of starting.
But as I said, that what I was reading, it was so that in these areas where they have this Nascadadi and Sutura and so on, it's very few sedimentary rocks.
Yeah, I was recently asked, people ask me if there is some maybe glacial diamectite or not where, but it's so deformed and so little studied that it's really hard to say. It could be like tectonical feature.
Yeah, but and of course for the Greenland, it's very well you can see, but then of course there's a huge area which is under the ice.
Mm-hmm. Yeah.
All right. Then with that, it seems like maybe people are satisfied. A good discussion. Thanks again, Raimo, for the presentation.
And thank you you for all, because you are having the morning, so you can't have a beer. But I'm definitely going to my
You
fridge.
can go and have a beer.
Is that a challenge, Raimo? That sounds like a challenge.
That's a challenge.
Okay.
All right.
Thanks, Raimo. Enjoy your beer.
Thanks. Okay.
All right,
see you.
everybody, take care. See you.
Bye-bye.
Bye.